So we got a test coming up on Friday, and what I was going to do today, I'm going to go through some Chapter 3 problems, I guess the last section too, and then before I start, does anybody have any questions about any problems, anything at all, before I get going on this? Nothing? Okay, well, good. That saves me time. So we did, we're starting into Chapter 3 in this book, and the only reason I'm using it is because the problems are a lot easier, and it makes the concepts, at least in my opinion, more understandable. We can get it complicated in a bit. We're going to go back to the book that was actually used in the beginning of the class. So I'm going to go through some problems at 3.1. We've already done these, I believe. Correct, class? But we're going to do them to make sure, because conditional probability and really joint density functions are something that can be very complicated. You're going to see in one section where we get the probability or density function for x given y or y given x. It gets a little crazy. So I want to make sure everybody's clear on this. Let's start with, we'll do this 3.1, 3.2, or 3, yeah.
Where exactly are we going to stop at?
This material. This is, I'm reviewing, I'm not giving you new material today. I'm just reviewing it. But you've had it before, the homework was there. I'm reviewing this, then, so it'll be through section 3.2 in that book, okay? Now, I'm going to go through 3-1 problems just because it's been a while since we talked about it. Then I'll go into 3-2 and I'll give you the theory behind it and apply it. You all with me on this, guys? Okay, let's try this, see if it works. All right. So this is, again, we're having joint density functions, and before I even start, I'm going to say this. Before, you're used to seeing something where you had like an f of x, a probability density function. It could be anything. And if this is x, you know that the properties were that the probability of x, and he'll always have this random variable, x less than or equal to x here, is really an integral, and it usually starts at minus infinity to x of f of x dx. That's just something that you remember talking about. This is usually given as f of x. It's a cumulative distribution function. Do you all remember this, class? And in the limit, as x goes to infinity, it becomes 1. The area under the curve is 1. That's all it is. So this is for a single density function. For a joint density function, if you talk about the probability of x less than some x and y less than some y, that's equal to a double integral. Technically, it's from minus infinity to some value x to some value y of f of xy, and here it's going to be dy dx. And that's just the probability density function, if it's a joint density function, of the value of x being less than or equal to a certain value and y less than or equal to a certain value. Now, again, as this small x and that small y goes to infinity, it's 1. The area under the curve has to be 1. Next thing after that, if I want f of x and I have a joint density function, then I can say that's equal to the integral from minus infinity to infinity of f of xy, and it would be dy. So I integrate out dy to get f of x. Do you all remember that? How many do? I'm looking and I can't tell for sure. Okay. And likewise, if we have fy of y, if we wanted that, it would be an integral from minus infinity to infinity of f of xy, and here we'd integrate out dx. These are just basic stuff, right? Now that I said that, and I want to get this all out here, let's do 3-1.1. I did these, I think all of them last night. And I was going through section 3.2 last night and this morning to make sure I didn't overlook anything. But that's the essence of what we're talking about here in section 3.1. So for the problem, this is problems in the back of the book, 3-1.1. You got it for me?
Yes.
I can hand you the book if you'd like.
I got it pulled up right here.
Okay.
So there's two random variables have a joint probability distribution function defined by f of x x comma y equals 0, for x
Yeah.
less than 0,
I got it. Okay, go ahead.
and y less than 0. And then for equal in x, y, it's x is greater than or equal to 0.
It's just xy,
Just x, y.
x times y, and this is for, and it's really 0 greater than or equal to x comma y less than or equal to 1, I believe, right?
Well, and then x is also less than or equal to 1.
That's what this means. It's,
Okay.
it's a joint, x or y less than or equal to 1. That's the only thing it means. I think he has, I don't know if it's the old book or this book that uses that kind of symbolism. But y'all remember seeing that? They would put like x comma y less than or equal to or greater than or equal to some value. All right, that's all it's talking about. So it only has values for positive values of x and y from 0 to 1, right? If you were to try to plot a density function of that, and I think he asked for this, if this is x, y, now remember it's 3D, right? Because that's a surface. Then what you'd end up getting is something that starts here and come up here, come up like, wait a second. Y0 is going to go away. Sorry, I can't do that. It would have a shape something like this, where it would peak right here and then come down. It would be like a, if you think about pinning one corner and then drawing a straight line to the far corner, all right? Out here, this would be at x, y equal 1. It would have a height there of 1, or yeah, it would be 1 right there. And just draw a straight line there would be like a tent draped over that, if you can imagine it. Can you all follow me on this, class? Okay, now, what do they want now?
There's another definition, f of x comma y when it equals 1, it's x is greater than 1y.
It's just for any value greater than x or y, 1 is 1.
Okay.
That's it. And oh, that's capital F of x, right?
Yes.
I'm sorry. So this is a cumulative distribution function. This is the integral from minus infinity to x, from minus infinity to y of density function f of xy. I'm sorry about that. Go ahead. Now, what does he want? The density function?
The first question is to sketch this distribution function.
I tried.
And then
It's just really a hint. Think about pegging 0, 0, 0, and then putting, a clothesline from that point to 1, 1, 1. X, y is equal 1, and then draping something on it. Yeah.
Will we have to do like a?
You're not going to have to draw it. It's a decent question. If I can't draw it, you don't have to. And I am not a sketch artist.
the next part is to find the joint probability density function and sketch it.
How do you, okay. Now, I didn't say this explicitly, but if this defines the cumulative in its two integrals, what do you think defines f of xy? It's really 1. It's a double derivative of capital F of, this is a cumulative distribution function with respect to x, with respect to y. That's the density function f of xy. That's the probability density function. It's a joint probability density function. You all follow me on this, guys? With me? So he made it as easy as he could. So what is small f of xy, the density function? Second derivative, right, with respect to x, with respect to y, of that, which is xy. It's 1, isn't it? That's all it is. Okay, how do you sketch that? Well, it's
Straight line.
it's just, well, this is a volumetric thing, right? I mean, it's a surface, really. So if this is x, this is y in this direction, right? It's just going to be a box of height 1, right? Y'all follow me on this, I think, right? That's it. So this would be f of x, y, it's just 1. That's the only thing he was trying to get out of that. You sketch it any way you want, but y'all with me? All right, what next?
Find the joint probability of the event capital X is less than or equal to 3/4,
Pay attention to this. Make sure you can do this without any problems.
and capital Y is greater than 1/4.
All right, let me go ahead and, so he wants the probability of, say it again, x,
Yes, X being less than or equal to 3/4,
comma.
and then Y being greater than 1/4.
All right, so this is 1/4 y less than 1. Okay. Really, you can make this greater than 0, less than 3/4, y greater than a quarter, less than 1/4, right? Now, you got the density function, it's 1. That's the easiest density function there is. Joint density is a constant, it's the easiest. So the only thing you do for this, you could do it a couple different ways. It'll be a double integral of f of xy. It's 1. That's all that is, right? We determine that. Then you put dx and dy. It's really this simple. This is the way I would do it. Now, x is the first integration. It goes from 0 to 3/4. And remember, this could be a function. I'm putting in a constant because that's what it is for ours. But it could be a functional form. And then y goes from 1/4 to 1. Well, this really is, if we integrate dx, we get x. Integrate dy, we get y. We evaluate them. So here, when we integrate, since dx is first, we just get x evaluated from 0 to 3/4 is 3/4. Do you all agree with that? When you integrate y, you get y from 1 to 1/4, or from 1/4 to 1, the way it's stated. That's going to be what? That's 3/4 too, isn't it? So it's 3/4 squared, or it's 9/16. Is that the answer he has, by the way?
I don't have the answers pulled up.
Here, you do now. I think it is. I did this. I recall some. Y'all with me? What's the next part of that problem? You don't have. Here, give it to somebody else to do.
I got it on my computer.
There you go.
That's
All right, what's the next part? Y'all follow me on this? It's that simple. Don't think, oh, it's too easy. And on tests, people get in this, instead of just doing what's asked, they try to think, it must be a trick, kind of. It's no tricks, just straightforward stuff on tests. Go ahead.
That was the last part of 3TAC 1.1.
All right, let's do the next. Are there any questions? This is a very simple one, just to get your feet wet. In the other books, some of the problems are much more complicated, and they take a lot longer. Remember that thing with the Merlot, Cabernet Sauvignon, and what was the other one? Zinfandel. And it was like one of these things where the permutations on that thing were getting astronomically large. Just with, even with a calculator, it was getting a little irritating. Next part, go ahead.
All right, 3TAC 1.2, it's two random variables, x and y, with a probability density function.
This is cumulative?
Yes, probability density function, lowercase f.
Oh, no, that's small f is the probability
Density function.
Okay, go ahead.
And then that's equal to k times x times y.
So it's k times x times y
For
x, y greater than 0, less than 1. I think this is it, right? He likes that area, which is nice. I like 0 to 1. And what does he ask for a value of k, I think?
And then determine the value of k that makes this a valid probability density function.
Okay, now most of you probably got this. Just work with me. How do we get it? How do you always get k if it's not given? If you have any density function, what do you know has to happen for it to be legitimate? Class? Integrate it over the range that it exists, and it has to be 1. If it's not 1, it's not a probability function. So if you look at this, if I integrate f of x, k times x times y, dx dy from 0 to 1, 0 to 1, I have to get 1. That's all it's saying. Y'all follow me? There's no tricks here. This thing can get as complicated as you want. It could be x squared, y to the 1/2. It could be 1 over x, y cubed. Doesn't matter. You have to integrate it and set it equal to 1 to get it the values of constants. That's what they're saying. If you take a look at this, what is this going to be? Well, it's going to be k, right? We can just write it down. Integral of x dx is x squared over 2. We evaluate that from 0 to 1. It's 1/2. Do you all agree with that? Integrate y dy, you get y squared over 2. Evaluate from 0 to 1, it's 1/2, right? So this is going to be simply 1/2 squared, or k itself is equal to 4. And that's the only, I think that's the right answer.
yes.
Okay, now, next part. If that is true, right? What does he ask?
He wants to determine the joint probability distribution function.
Oh, he wants f of x.
Yes, capital F of x of y.
Okay, so now how do we get that? Now think about the definition. So f of x, let me put it here. Capital F, this is the cumulative distribution function, f of x, y. It's always a double integral, starting at technically minus infinity to x, minus infinity to y. The order is unimportant, of f of xy, which is now 4 times x, right, times y, and we can go dy dx. The order is unimportant. You all follow me on this? Now, what do we do to make sense of this lower limit? You see how this is only, it's 0 for any values outside 0 to 1. Do you all follow me? So I just set the lower limit to 0 instead of minus infinity. Technically, it should be minus infinity, but since it's 0 until you hit 1, or hit 0, I just go from 0 here and 0 here. So that means this f of x, y here is going to be what? Well, it's 4. You integrate, and technically, I didn't do this, but these should be primed, right? Because technically, you can't integrate, you can't have a kernel of integration that has any symbolism that has to do with the limits. Do you all follow me? Technically, you should prime. That's the only thing I'm doing. In real world, when I do this in my notes or something for something, I don't do those problems. I know it's just a dummy variable. It's integrating. So you get this. You're going to get x prime, or I mean y prime dy prime. You get y prime squared over 2. From 0 to y is just what? Y squared over 2. And for x, it's x squared over 2. So here it's just x squared y squared is capital F of x comma y. And this is true for 0 greater than or equal to x comma y less than or equal to 1. And it's 0 everywhere else. That should be the answer, I hope. Okay, what's next?
It wants to find the joint probability of the event that x is less than or equal to 1/2 and y is greater than 1/2.
All right, guys. So he gives us a range, right? Now, you could use this, but here's the way I like to do it. Say it again. What was the range?
X less than or equal to 1/2 and then y greater than 1/2.
Okay, we could use this to get it. But this is just me, and I prefer to do this. We have this right here, right? So if we have that density function, just use the density function, integrate it over the range. You won't mess up this way, in my opinion. So now I know my density function, f of x comma y, is really 4xy. And this is from 0 greater than or equal to x comma y less than or equal to 1, and it's 0 else. That's the only area I care about, right? So go ahead, and we want the probability of, say, of x less than or equal to 1/2, was it, or what?
Yes, 1/2.
And y, better put it here, y greater than,
1/2.
all right, less than 1, right? Those are the limits. You simply define the integration here. So here we're going to have a double integral. Of that, it's 4xy. It's dx dy. Here, x goes from, I didn't put the lower limit, but it's from 0 to 1/2. And y goes from 1/2 to 1. So if you integrate that thing, I have 4 out in front. Then I integrate x dx is x squared, right, over 2 from 0 to 1/2. So it's going to be 1/2 here, and then I have simply 1/2 squared. That's simply 1/2 x squared, where I replace the x squared by 1/2. Do you all follow me, class? Take a good look. Make sure that you see it. This is only the x integration, right? Now when we integrate y, we got y dy here. We're going to get y squared over 2, correct? And we have to evaluate it over this range. So we get another 1/2. And then we evaluate it. Well, that's 1 squared is 1 minus 1/2 squared is 1/4. Now just take a look. Make sure you see what I'm doing. There's nothing tricky. I'm just trying to state it. Do you all agree with that? Can you see it in the back, by the way? All right. Here's what I would do if it was me. I got 1/2 squared and 4. Might as well get rid of that. Make my life easy, right? I got 1/2 times 1/2, that's 1/4. That's why I like whiteboards. If you ever get a chance to bring a whiteboard at home or something, if you're doing problems, especially with people, this is great. So now I have, this is 1/4, right? And 1 minus 1/4 is 3/4, so it's really 3/16. Is that right, by the way? Y'all with me? And that's, what's another part to that problem or no?
Yes, it's find the marginal density function
Of,
of f of x,
Let's do it.
fx of x.
okay. All right, guys. So now he's asking for, let me erase that too. Are there any questions before I go? There's really no tricks here, right? Just know the range of integration, take the density function. It's a done deal. And it could be, you can get odd ones. Suppose I say I want this for x greater than 0, less than 1/8, or greater than 3/4, less than 1. Then you would have two portions of the integration in dx. Do y'all follow me? With me?
So what would you do if it was an or statement versus and? Like what would be the
Or,
difference?
well, I mean, if you said, now this is the thing, if you said you wanted the probability of x being greater than 0, less than, say, 3/8, or greater than 3/4, less than 1, then you would have to do both of those integrations when you integrate dx. So it would be a two-part integration kind of deal, but they would be added.
Added
'Cause
together.
it would be added,
Okay.
right? Okay. Back to this thing. So now, how do you get, here's our density function, f of x, y is equal to 4xy for 0 greater than or equal to x comma y, less than or equal to 1, right? 0 else. Now, he wants just f of x, is that right?
Yes.
How do we get that? Yeah, now you integrate technically over the range that exists, but in ours it's 0 to 1 of f of xy or 4xy, and this is going to be what? dy. We integrate out dy. Y'all follow me? When you do this, what do you get? Well, you got 4x, that doesn't change. Y integrated is y squared over 2 from 0 to 1 is just 1/2. So it's this times 1/2, or it's really what? 2x, and this is for 0 greater than x less than 1, and 0 else. Does he have that, by the way? I'm assuming he does.
Oh, I'm sorry.
That's all right.
Yeah, it's 2x.
Y'all with me? What would it be for y? Fy of y.
2y.
Now, it's in the chapter, in this section of the chapter, I believe, but I just want to complete the thought with what if they wanted the probability density function for f of x given y. Hear me on this one, everybody? We covered this. If I wanted f of x given y, this is the symbolism. It means y is set. You don't know the value, but it's set in stone. You with me? And you want this. Well, that is technically equal to f of x comma y. So it's a joint density function. And then it's divided by fy of y. That's the density function of f of x if y is stated. It's tacked down. Now, I got to say something else, too. It's in the book, but this is an important concept. And this Bayes' theorem can be put so many different ways. But if you look at f of x given y times dy, it's the same thing as f of y given x dx. Those will be the same. And well, let me say this. In his book, let me do one thing about this. I want to show you where this is in the book. And because I want to be clear about a couple of these things. Some of the stuff's going to get a little confusing. He's got it earlier, I think. Maybe, I think it's in a prior chapter, but it's not stated this way. I'm sorry, he does it with the f of y, so let me rewrite that. This is, the one thing I'm looking at is right in the center of page 127. Or actually, it's equation 3-14, but he does it a different way. So let me just put this down without the dy and dx. That was not right. So if you have f of x given y here, times f of y, fy of y. That's the same thing of f of y given x times f of x of x. Now I think he shows us with one of these things, like if you look on equation 3-14, he doesn't multiply them like I do. I like doing it that way, but it's essentially the same thing. Y'all follow me in this class? Now, something else too, and I'm trying to think of if he shows you this, because this is important. Yeah, this is equation 312, and he shows you f of x given y is equal to f of x comma y. That's the joint density function over f of y. Now remember, y in this case is known. It says if we know y, so fy of y here would be a known value. It's the joint density function there divided by this. What this does is normalize the joint density function, so when you integrate it over the range, where y is defined here as a single value, of x values, you're going to get 1. That's the only thing this does. Y'all with me on this? Do you remember me putting this up? It's been a long time, but this is when on the board in class. Does anybody remember that? By the way, that camera I had at home for Zoom is fixed. It was a pain in the butt to do. Y'all with me on this class? All right. I just wanted to complete that. We did 2, right? Let's do 3. I'll come back to that in a second, but I want to make sure I at least touched it right there. So this is 3-1.3, I believe. Go ahead.
And so this is going to be using random variables from the first question, which are
F of
x comma y.
is 1. I mean, this is a density function is 1. The cumulative distribution function is x times y.
Yes, x times y for
I'm going
X
to just
and-
leave the density function. It's 1 between
0 and 1 for x and y.
0 greater than or equal to x comma y less than or equal to 1, and 0 else. Go ahead.
And it wants to find e of x and
Expected
y.
value. Expected value of what?
X times y.
All right, this is it's simple. Now they want the expected value of a function. He defines a function as just x times y. It could be any function, right? It could be an exponential, could be anything. Well, the only thing you do is we got the density function at 0 outside that range, so you take this and do a double integral. Now you take the function, which is just x times y here, and then you multiply by the density function. It's 1. Y'all follow me? Now it doesn't have to be, but here it is. And you put dx, dy, and you have to integrate this over the range of existence, 0 to 1, 0 to 1, where it's non-zero. Y'all follow me? Now that's it. But you can see this can get pretty complicated. First of all, this functional form here, the expected value, suppose you have e to the minus 3x times y squared. Now you're going to have to do those integrals, and it gets a little more time consuming. Then you could have something where it could be over, I mean, suppose this range was not just constant over that range. I mean, suppose that density function was 1 between, say, 0, xy less than or equal to 1/2, and then it's some other value between like 3/4 to 1. You all follow me? Then you would have a more complicated integration to perform. But the essence is the same. You take the functional form, multiply it by the density function, then integrate over the range the density function exists. That's it, where it's non-zero. Here, what's it going to be? Well, x dx is x squared over 2, right? From 0 to 1 is just 1/2. Do you all agree with that? Y dy is y squared over 2. From 0 to 1/2, it's going to be 1/4, correct? I mean, sorry, it's going to be 1/2, so 1/2 times 1/2 is 1/4. Do you all agree with this? So this should be 1/4 for that problem. Is that right? Pardon? With me? What else does he ask for? We can do some crazy ones if you want.
This is for the random variables of problem 2.
Hold it.
Isn't that what we just did? Or was that problem 1?
That's for the random variable problem 1. The density function, the capital F of xy was x times y. Then small f, the density function was the derivative of that with respect to x and y was just 1.
Okay.
How many remember that? y'all remember that over there? The far wall? Okay. Y'all with me on this? You good with this? Yeah, I'm making sure, because whenever I get these odd looks sometimes and I don't know how to read it, it's like, of course we do. Do we look like idiots? No, but sometimes I feel like an idiot up here. But go ahead.
And he wants us to do the same thing, find the expected value of x times y
For that problem?
for the variables of problem 2.
All right, so this is part A of this. Part B, the density function f of x, y for that problem, you're going to have to help me.
It's equals k times x times
4
y.
times xy, right?
4xy.
So it's 4xy, and this is for 0 greater than or equal to x comma y less than or equal to 1, and it's 0 else, of course, 0 else. I'm just restating it, right? So here, y'all follow me? Just let's do it. So what's the expected value that's going to be?
Expected value of x times y. So it's the double integral
Of,
4 times x times y.
I want to make sure I put this down, times what? X times y, right? Follow me? So this xy is a function, the density function is here, 4xy. Y'all follow me, class? Just to be sure. Now you put the limits in. From 0 to 1, 0 to 1. Okay, I'm going to put the 4 out in front. What happens when we get, now we have x squared dx, don't we, class? I got x here, it's x squared dx is x cubed over 3. From 0 to 1, it would be just 1/3, do you agree? Then I got y squared dy is y cubed over 3. From 0 to 1, it's going to be 1/3 again, so it's 1/3 squared. So this is 4/9, it looks like. Is that right? Y'all with me?
So for the first problem we did, when we were just doing the variables from the first question,
The density function was constant. F of xy, the probability density function was 1.
just 1.
So it's x times y. Here, the density function isn't. The density function is k, which is 4 times xy. So x times x is x squared, y times y is y squared, right? I mean, I let us think and dealt with, I mean, this is not meant to be tough. And I like the one thing about this book, it's very simple problems to see the concept. We can complicate it in a heartbeat, but for now, we're making it simple.
As long as you put simple ones on the test.
And that is in the eye of the beholder, right? Like beauty. All right, what's the next part?
The next question is 3 Tech 1.4.
What, isn't there another part to this?
No, that's everything.
All right, we might as well just talk about this one. Let me erase this, hold on. I got to tell you guys one thing. So years ago, I taught this, what is it called? It's 3810. It's really electrical engineering, electronics and circuits for non-EEEs, right? So in Irwin's book, all the problems are like this, right? Kind of deal, you know, where they ask for the resistance. Y'all with me on this? So on the test, I did this. I put, and I asked the resistance. This one person was furious. You never showed us a problem like that.
You gotta be nice to them, because like, they're nice to us over in Thermo land.
I got to tell you something, all right? Now, I didn't say anything because sometimes you have lapses, you know. The wire is just a wire, doesn't matter what orientation has, but I didn't. But before that, something happened that really, this one got me. Now remember, we had a lot of people transferring into this program from community colleges. In community colleges, they got these exams that are just multiple choice, right? Now a lot of times you can just look over your neighbor, if he knows what he's doing, you can. So I hope I didn't say this to you. This is a true story. I know, I'm not going to mention the student's name. I'll never forget this. So I said that Q of t is the integral of I of t dt from minus infinity to t, right? What's that big S you put on the board? I thought he was joking. It's an integral. What's an integral? We need to talk. He was serious. That's a true story. I have found things like this, and I'm not kidding about that. It's rare, but you know, people can sneak in the door somehow. And
Is there any chance you're putting formulas on the test? Like,
I'll give you the permutation ones and stuff like that. I'll give you those. Remember, I did that on the quiz, the permutations. I'll give you that. I'll give you like the. You know, when we talk about what? P of k comma n factorial over n minus k over k factorial, p to the k, and then it's going to be 1 minus p or q to the n minus k. I'll give you that. All right, I'll give you the permutations. I'll give you the combinations and stuff. I'll give you those. All right.
Like not the equals.
Of
Well,
what?
the density, like density functions of like certain distributions.
Gaussian, you mean? I'll give you Gaussian.
Okay.
All right. I mean, I'm going to give you tables if you got to look up stuff. But let me get there after I do these. And I just want to tell you, I'm not going to let people worry about calculating like Maxwell integrations or anything like that, or stuff like that. Rayleigh are the easiest, by the way. Rayleigh is easy because remember, Rayleigh distribution, it's really R over sigma squared, right? And that's Gaussian sigma squared, e to the minus R squared over 2 sigma squared Gaussian. When you integrate that, you just get 1 minus that e to the minus exp to the minus the value R squared over 2 sigma. Remember that? It was easy. We'll talk about that in a bit. Let's do this one. Go.
All right, 3 Tech 1.4. Let X be the outcome from rolling one die.
I didn't do this one. All right. More
And
dice.
Y be the outcome of rolling a second die.
All right, this is dice. So this is an outcome. Y is outcome of rolling a dice again, right? Go ahead.
And then find the joint probability of the event that X is less than or equal to 3 and Y greater than 3.
Okay. For this one, what is the density function f of x? It's really what? He calls it a instead of a probability density function, it's a probability mass function, remember? And if you look at this, if this is the value of rolling the dice, right, itself, the density function, well, let me think about this. It's going to be 1/6, pardon me, 1/6, 1/6, and it's just going to have a whole bunch of these things that are all one, and you're going to have 1, 2, 3, actually, yeah, there's no 0. 1, 2, 3, 4, 5, 6, right? All with a value of 1. It would be a probability mass function in the old book. Do you all remember that? It's just like a density function on their impulses, correct?
The only probability of 1 or 1/6?
1/6, right? Got to be 1/6, doesn't it?
Yes.
Because the integration, or in this case, the summation of this has to be 1. That's the idea. What about the other one? Same deal, both of them, right? So what's the joint density function for these? Is that what he asked for?
The joint, he wants the joint probability of the event occurring that X less than 3 and Y greater than 3.
All right, so this really is just going to be 1/6 squared or 1/36, all right? We could map this out. If you think about this, just try to bear with me. If you had a 2D grid of X, Y, and right in here was a probability density or probability mass function for this, then there would be points. If this is 1, this is 1. So if you're looking straight down, you would have points here. Each one, there would be 36 points, and the height of each one of those points would be 136. Does this make sense to everybody? Y'all with me on that? Now, what does he ask for? I'm going to try to show you that. So understand that this is just a whole bunch of 136 spikes, impulse functions. I'm just trying to show you. Go ahead.
Is that the joint probability of the event?
136. Is that, does
For
he
X,
show you that?
for X less than 3? And
No. This is the density function. Now we'll get the probability. Y'all agree with the density function in your class? All right, now we want the probability of what?
X being less than or equal to 3.
x less than 3, right?
And y greater than 3.
What, less than or equal to, and comma, y what?
Y greater than 3.
Greater than or equal to 3?
Just greater than 3.
Greater than 3, okay. All right, if you think about this, what are we really doing? Think about what that area is. Here, for x less than or equal to 3, call that x, so here's 1, 2, 3, right? That's this range, right? Y'all follow me? What about y greater than or equal to 3? Remember, we're limited to here. Y are greater than or equal to 3. Well, if this is,
It's just greater than 3.
or greater than 3, so if this is 3, it would be 4, 5, 6. Do y'all follow me? So this, the amount of those dots, just count the spikes in that region, would be that. Do y'all follow me? That's the way I think of it, and it's easier. So how many are there? Well, 2, right? Here, it's what? 2, correct? 4, 5, or 3, I'm sorry. 2 times 3 would be 6, right? But the height of each of those is, yes, sir.
Shouldn't it be 3 on the bottom there since it's less than or equal to 3?
Here's 1, 2, 3, isn't it?
Okay, so
Oh, I'm sorry, the spread is 3. That's what you're saying. I'm sorry about it. So it's 3. The spread here would be 4, 5, 6 is 3 as well. I'm so sorry about that. So it's going to be 3 times 3 is 9 times what? 136, right? So this should be 9 over 36, and what is that?
1/4.
1/4, is that right? Yes. All right, but you'll follow me the way I'm doing it. I like doing this with getting the density function. And remember, these are mutually exclusive, so there's no overlap. You roll the first dice, it has nothing to do with the second dice, you roll the second dice. Then you can think about the density function I've showed you there. Does everybody follow me on this? What else does he ask?
Find the expected value of x times y.
Over the entire range?
He just says find the expected value
Okay,
of
it
x
has
times
to
y.
be, right?
Yeah.
So what is that going to be for this problem? Now look, it's the expected value of x times y. Normally what? We have integrations. Here, we don't. We have summations, right? So we're going to have the expected value, and I'm going to take the density function out in front. It's just 136. That would be the probability density function, joint probability density function of xy. First dice 1, second dice 1, the probability is 1/32, right? Or 36. Correct, class? Then you do the sum of what? Sum of x for x equal 1 to 6, and it's times the summation of what? Y from y equal 1 to 6, correct? Now, you'll notice those two are going to be the same thing, isn't it, class? So what do? You're going to say this is 1/36 times the summation of what? I really can go x equals 126 squared. And what's that going to be? You can do it in your head if you want. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, right? Plus 6 is 21, isn't it, class? So it should be 21 squared over 36. And what is that? I don't know what that is. Is that what he has? 49 over what? Over 4? What is the value of the number? All right. Does that make sense to everybody? And I always prefer, now you can fuss with these cumulative distributions and get some of this information, but I prefer the density functions always. It's easier to see, easier for me to explain. Is there another part to that one?
Yes, find the expected value of x given y.
X over y?
X over y.
That's not given y.
Oh, it's not given y?
Capital F?
No, capital E of
Yeah,
x
that's an
over
expected
y.
value. That's expected value of y over x. It's a derivative. Y'all follow me? Divided by. It's different. So here, now pay attention to this, because this was a straightforward one. And this is straightforward too, but you're going to have to follow me. So really, now the expected value of x over y. Remember, The density function is just 1/36 for every possible value. So I'm going to take that out in front of this summation. Normally it would be inside the integration would be the density function. Then you put the actual function you want the expected value of in there. So I'm going to say this is going to be 1/36. That's just the density function. Now I have to sum up, and I'm going to do on x first, from x equals 1 to 6 of just x, right? That was 21 last time, if you remember. Then I have to sum up what? And multiply. Now I have to sum up 1 over y from y equals 1 to 6, right? All right, so this is going to be 1/36. Now we just did this. If we go from 1 to 6, we get 21, don't we? Y'all with me on that? So that's 21. What about this one? I got what? 1 plus 1/2 plus, this is a famous one, 1/3, right? Plus 1/4 plus 1/5 plus 1/6, right? Now you can get a common denominator. What is it going to be? I think it's 30 in this case, isn't it, class? So what do you get? You got over 30, you would have 30, right? Plus 15, right? And then plus 10.
I don't think 30 is.
It ain't 30. Anyway, can somebody just do this for me? Sorry.
2.45.
2.45. And so that means this becomes 2.45. And what's the value? But y'all follow me what I did, right? What is that? I don't know.
Oh, the final answer is 1.42.
Can you go ahead and multiply it? 21 times 2.45 over 36.
It's 1.429.
Is that right? But y'all follow the, does everybody understand the method? They're disjoint so I can decouple them like this. There's no, one isn't dependent on the other. Okay?
We're never going to be asked the expected value of something given something. That's just not something we.
Yeah, we could do it. We're about to get, you remember we did conditional probability back in chapter 2? Assuming a dice roll is greater than 1, what is the probability it's 2 kind of deal? Do y'all follow me? There you limit the value of possibilities, right? Do you remember that? I mean, this is, we had the Venn diagrams, right? A, if we had A occurred, what's the probability of B? It's the ratio of the area of overlap of an A and B over the total B kind of deal. Do you remember that back in the Venn days? Okay. All right, now, let me give you a little background in the next section. I think I started this, but I didn't go through it, so I'm just going to finish it right here, get it done. And again, I say this a lot, but the only thing I'm going to do, really, the test is based on the homework. Think about your quizzes. The quizzes reflect the homework, right? The tests will reflect the homework. They're not going to be exact, and they may have lines going diagonal instead of vertical, but they will be basically something that's derived from the homework. If you understand the homework well, you'll have no problem with the exam. But if you're confused, then you might have a problem. Okay, so give me 1 second. Now, this is conditional probability. I've already alluded to it. We're going to give an example of this. So with conditional probability, it's like if they assume, for instance, if you have a joint density function, and now this is a probability density function. Here it's continuous, but it could be just a probability mass function where they're discrete values. And now you want the probability or the probability density function for x specifying a y. Well, I told you this already. If I take this times fy of y, that's the same thing as fy of x, specifying x times fx of x, right? Does everybody follow me on this? Now, what is say y given x? Well, that's the joint density function of f of xy over fx of x. Here, This means x is specified, is known. That's the one thing you take away from this. So here I'm going to tell you that I'm going to try, I've thought about the ways to do this effectively. So this is section 3.2 in the book, and the best possible way that I can think of is with a couple of illustrations, a couple of examples. So a very common thing that happens whenever we measure signals and stuff is we have noise. So if you have a function where you're measuring a signal and it has noise, suppose y is what you're equal to, you can measure. It's equal to x. That's a voltage, but there's noise in this voltage, plus n. So you'll see this in his book. It says the output y, a measured voltage, is an actual voltage in there that we have the statistics for, plus a noise that we have the statistics for. You all with me? And he gives some examples of this. But before I say much about this, well, if you take a look at this right here, there will be an f of y. There will be an f of x comma y, and an f of the noise as well. But if I say I want f of x given y, y'all follow me on this? So I would like to have an estimate of x, assuming I know y. I measure this, I know it, but I know there's noise. Well, technically speaking, and I'm going to try to do this. It would be f of x comma y. This would be equal to, and let me try to do this. Since y is known, if I look at this for a second, bear with me. Y is going to be given on this one. You all with me? So if I have y minus x, since y is known, that would be the noise. Do you all follow me in this class? Now the noise is going to have a distribution. I'm going to put it up here. Fn of n is known. It could be any function, doesn't matter. So Fn of y minus x right there, if you look at this, since y is known, that gives me the relationship of the density of x. If you can think about it this way, listen, if y is known, then the noise is the only thing that's random. That's the way he talks about in his book. Does this make sense to people? So if you look at this, if I give you y, I can plot the density function of x for all values of x just by finding f of n and replacing the n in there by y minus x. And then I could literally plot that if I wanted to. Now I could plot, and you can call this, because y is known, you can call this Fn of y minus x is, and this would be the, quote, f of x if y is given, right here. And it doesn't matter what it looks like. It could have a skewed value like that, but you'll know that. So now this says that this is equal to f of y minus, or f noise of y minus x over, and then it would be times, and then it would be an integral here from minus infinity to infinity of f of n of y minus x, f of x, no, f of y, pardon me, dy. Let me stop there for a second. Pardon me?
You put x dx. Oh, for the integral?
That's,
Yeah.
oh, let me get this. You're right. Wait, this should be the top portion itself. So it should be the integral of f of n of y minus x times f of x dx, I'm sorry, from minus infinity to infinity. And that will be the value of f of x over y. And I want to say one thing about this, because some of you are thinking, are we going to be required to do this on a test? You won't. because that's a logical question that probably everybody has, is what you're responsible for, because the test. But I wanted to show you this, and I'll tell you where this stuff is discussed in your book. Some of this stuff, it's going to take me a while to explain it all, but this is on page 126 of the old book, 127, 128, 129. I think I'm going to do one thing because I only have 15 minutes. I'm going to stop there. You won't be responsible for section 3-2 in this book on the exam, but everything up to 3.1, all right, through 3.1. Now, what I wanted to do is the last 15 minutes is answer any questions about problems, anything like that on the exam, and we might as well put down like the combinations and the binomial stuff. So I'm going to start over here. We can do some problems with it. I wanted to go through that today, but I'm not going to have time to explain all that stuff, I don't believe. So back to so if we have events and we want to know the probability of, it's going to be capital P here, of taking K items given N things, and this is a binary kind of deal, right? If you have like 5 coins and you toss some probability heads, tails kind of deal. So this is always going to be equal to N factorial over N minus K factorial. K, of course, is going to be, K itself is going to be less than or equal to N over K factorial. Then it's going to be times the probability of event occurring. This is event occurring right here. And it's to the K times 1 minus P, or Q, to the N minus K. And that's it. And what it really is a probability of an event occurring, right? So the typical thing is the coin toss, where the probability of heads and tails are half, right? But it doesn't have to be. Again, these are binary decisions, right? Either it occurs or it doesn't occur. Y'all follow me on this? So the probability of getting 0 heads in 3 attempts is a typical one, right? And we'll do 2 heads too. So that's going to be equal to, the N is 3, so it's 3 factorial. N minus K, since K is 0, is 3 factorial. K is 0, 0 factorial is 1. And it's going to be times 1/2 to the K, which is 0, times 1/2 to the N minus K, which is 3. So here it's simply going to be 1/2 cubed, or 1/8. And that's classic, right? And you all know that. I'll give you the binomial. I'm going to tell you that because you're asked. Somebody's going to ask. All right. So what's the probability of 2 heads in 3 tosses, class? Over?
3 minus 2 factorial, 1 factorial,
This is going to be 1 factorial and
2
2
factorial.
factorial times, this will always be just 1/2 to the N power, right? Doesn't matter because the probability of heads and tails is the same. So it's just going to be 1/2 cubed, right? So what is that? It's 3 divided by 2 cubed, so 3/8. Do you agree with that?
Wouldn't that be 1/2 squared?
Oh, sorry. Right here, my bad. Let me do it this way. So when you do this, it's going to, probability of is 1/2, and that's squared. Then it's going to be what? 1/2, right? 1 minus 1/2 is 1/2 to the 1, right? So it's 1/2 cubed is what I'm getting at. That's always going to be this. So this is going to be 3 over 2 cubed is 3/8, right? What about 3 of 3? Same as 0 of 3, right? 1/8, right? Y'all with me on this? So this is just showing you the probability of these events occurring. Now the cumulative probability is 1. If you talk about combinations versus permutations, do you remember the wine problem with Zinfandel, Merlot, and Cab, right? There were 2 things you had to know. And I don't have my old book here, but does anybody have the older book? I wanted to get the page number for this. So when you talk about permutations versus combinations. The permutation right here, if you have Kn was equal to n factorial over n minus k factorial. Do you remember that? That's basically something where the ordering becomes important in this one. Do y'all remember that class? Now, this is permutations for combinations of Kn. Now the order doesn't matter, right? That's what? It's the same thing as this. It's n factorial over n minus k factorial, but then there's a k factorial. Do y'all remember that? That's the only difference. I'll give you those things. The Merlot problem, the Merlot's infidel cat problem was great at really illustrating this. Do y'all agree with this, class? All right. I wish I had that old book with me. I didn't bring it. But it's in here too. So just don't, it's all right. Let me go through this. Now remember with the density functions, the ones where they're probability mass function, we had, basically impulse functions dictating the probability mass function, not continuous. Remember those problems, they're basically things that had to do, he terms it counting, how you can take variables in a certain order, right? If they were ordered, if it's ordered, then this is the one that you apply to it in terms of the number of possibilities. And if it's unordered, it's this. Do y'all remember that class? That's the only difference, ordered, non-ordered. And that problem's a good one. Back to the density functions we talked about. I want to just mention this because you have to know how to get the expected value and stuff like this. We talked about the constant density function, probability density function, with just a constant value over a certain range. And we got the expected value, we got all that business. We talked about the exponential density function, right? We talked about chi-squared. I'm not going to hold you responsible for chi-squared on the exam. All right. Then we talked about Rayleigh. You are responsible for Rayleigh. And we talked about Maxwell. We talked about the Gaussian. Gaussian is something you're going to be expected to understand well. And I'll give you tables related to that, but your calculators will do it too. If you have any modern calculator, you can use that. Remember that quiz I posted, the tables? So problems related to that kind of information in the book. And it could be on either book. And the Rayleigh density function. And remember, there were a lot of problems where, like, you had something where velocity in marbles, x and y, or shooting an arrow at a target and distance from the bullseye, right? Now, we'll talk, I want to do one of those in a second, but I'm just giving you an idea. For Maxwell-Boltzmann density functions, if I ask you anything about them, I'll provide the density function for you, all right? But I'm not going to provide the Rayleigh density function. Well, I'll provide the Gaussian density function. Here's what I'll show you what I'm talking about, so you'll not have a problem.
You said the chi distribution will not be on the...
Chi-squared.
That won't be on?
No, the reason is frankly, it's going to take too long to really do justice to that if you're going to be calculating. Remember how crazy that thing was? If you don't, you haven't done the homework. But I'm almost thinking just sort of to keep it light, to give you a problem with Merlot's infidel and cab again, just because.
I wouldn't be mad about that.
What do you want, beer instead? Or?
No, I like that. I like the problem.
Okay. I mean, the guy, you got to figure this guy's not too far out of college. Beer, cabaret, food. I mean, wine, beer, food.
He knows his audience.
Tailgate tickets, who knows? Okay, so the next thing I want to talk about is, here's what I'm going to give you. So if it's Gaussian, all right, then the distribution, we'll call it f of x, if it's Gaussian right here, is going to be equal to 1 over square root of 2 pi, right? Then sigma, this is a Gaussian sigma, exp, right? Minus quantity x minus the mean value of x squared over 2 sigma, and this is Gaussian squared. Y'all remember that? So that's the density function. Then if you use the tables to get information, do you remember how now when you take a look at the integration of this, right? If you integrated f of, this is the Gaussian of x, and you had dx from, say, yeah, let's go from minus infinity to x, or we could go from x to infinity right here. In the book, this is the characteristic function, right? Do you all remember this? But he does something about this. He says what this is really going to be is the characteristic function where we take the argument and say x minus x bar over sigma Gaussian, right? Do you all remember that? You had to normalize, you have to subtract off the value of the mean and then divide by the standard deviation, the Gaussian standard deviation. Do you all remember doing that? This is for the characteristic function. And that characteristic function is what? It's 1 minus the q function of x minus x bar over sigma. Do you all remember that? We had q. They're related. The q function just goes from x to infinity. The characteristic function goes from minus infinity to x, but they're the same value, and it's really a probability kind of deal, right?
What's that symbol you wrote?
Q. Do you all remember those things in the back of the book? And I provide you one of the, either characteristic or Q function tables. One is the same as the other. Okay, that's it. So if I asked you, let's see. Well, you can look all this up, so we'd need tables to actually do it. But your calculators, I believe, do this. I know yours does it, and yours does it. And probably all of your calculators do these kind of things. Now, that is just stuff for Gaussian. We can. It's pretty straightforward, but we can do some problems. For Rayleigh, do you remember the Rayleigh distribution was the easiest one, in my opinion. So, and we'll talk about a problem related to it.
What about Erlang? Wasn't there like Erlang?
Isn't that related to chi-square? Do you all remember that? You don't worry about Erlang. That's really for, actually. It's exponential, but it's not one exponential. It's multiple exponentials. The probability of it's busy at least 3 times in a certain interval, but it's the exponential decay. But don't worry about Erlang. I'm not going to get you on that exponential single event type thing. You should know though. Okay, so now this is the Rayleigh distribution. So here, the density function, and I'll call it f of r, is really going to be r, the variable, over sigma squared. That is the Gaussian sigma, not the Rayleigh. Remember that. And it's times exp. And here it's going to be minus r squared over 2 sigma squared. Do you all remember that, class? Remember, Rayleigh is strict positive. The typical thing is like the Archer. Here's where it comes into. If you think about this, where this is x and this is y, and this is the bullseye, the distance r would be the square root of x squared plus y squared. So if you had a Rayleigh distribution for the probability of the arrow hitting the target center, it was if the actual density function was Rayleigh distributed, and you want the probability of the arrow being between one and another radius, then you would integrate this density function. If you wanted, say, the probability from R1 greater than or equal to R less than or equal to R2, it's the integral of this, which is the integral of R over sigma g squared exp to the minus r squared over 2 sigma squared, Gaussian sigma, of course, dr. And I should prime those. And it would go from r1 to r2. And what that amounts to is this. The probability it goes here, this is going to be 1 minus exp to the minus r1 squared over 2 sigma Gaussian squared. It's that minus, and then it's going to be 1 minus exp to the minus r2 squared over 2 sigma Gaussian squared. Now, I wrote it down entirely. when you integrate this thing right here, you're going to get 1 minus exp to the whatever the values are. If it goes from 0 to R1 or I should call that R2, and this should be R1. Pardon me. Where this is further away, then you go from 0 to R2 is this value. You all follow me, class? I'm being a little. I'm trying to. So this is the probability that it's between 0 and R2. Then I subtract off the probability it's between 0 and R1, the lower one. Do you all follow me? What can you see happening there? Well, it's really what? exp to the minus R1 squared over 2 sigma Gaussian squared. That's this one, right? And it's going to be minus exp to the minus R2 squared over 2 sigma squared. Do you all follow me in this class? The ones cancel. You with me? Here, I'll get out of you. So that would be it. For Rayleigh distributions, that kind of information's useful. There's what is the Rayleigh mean in terms of the Gaussian? Do you remember that? Square root of pi over 2, right, times Gaussian. How about if I give you that? I have a feeling you'd mess up. People are going to make mistakes with that stuff. I'll give you the mean for the Gaussian, and I'll give you, the mean for the Rayleigh based on the Gaussian sigma. Okay? Fair enough? You can mess that one up. Now, we could do some problems on this. I think I'm out of time, but does anybody have a problem they want to see worked again? It's been a while. We had, what, one lecture last week, and the week before we took Friday at the beach or whatever. I did a Zoom that wasn't so Zoomy, but you all follow me. We didn't have much class in the last 2 weeks. That's one of the reasons I want to go through this. Now, as far as the other stuff that we've done prior to that, you remember we did Maxwell-Boltzmann, we did exponential, we did constant, right, a constant probability density function. We did Gaussian, of course, Rayleigh. Trying to think what other ones. We did all those counting things, and we did Venn diagrams. I think you guys are ready. As far as, yeah.
What about log normal?
No, you're not going to get log normal. Because think about calculating it. It's a pain. Here's what yeah.
How many questions and how many parts to each question?
Okay, who's had me before? How many problems are usually on an exam? How many pages? Well, 4 to 5, and typically they're multiple parts. For instance, if I give you one page, it'll have a problem statement. Think of the Merlot deal, all right? All right, so all this wine, how do you take it? And remember, there are 3 or 4 different parts to that one, what I asked for. So it's usually what I do. It'll either be 3 or 4 problems, and there'll be multiple parts. But they're very similar to the homework problems. If you look at the homework, they're all multiple parts, just the ones we did today, right? Just think of, yeah. Quizzes are a little shorter, obviously, but, we got an hour and 15 minutes for the test. If you know what you're doing, you should be done in an hour, probably in 45 minutes, no problem. But there are people that always second guess themselves, and I understand. I was sitting where you were long ago, and I appreciated not being pressed for time. Some professors would press you with a lot, more or less. You really had to be sharp and moving quick to finish it, but I don't try to do that, not intentionally anyway. You good with that? All right.